Today we are going to start a new topic, generalized coordinates and coordinate coupling. And this is the last set of lecture notes that I will be giving to you. That is lecture note set number 24. Now, let us understand what is the meaning of a generalized coordinate. Coordinate coupling will come after that. See, if you read it from a book, the basic idea you'll get is that generalized coordinates are those coordinates which give you the configuration of a system at any instant of time while the system is in motion. Now, if you reflect back on something that I have taught you earlier regarding degrees of freedom, that also goes by almost the same definition. So if I reiterate the definition of degrees of freedom, I would say that degrees of freedom are actually the number of mutually independent coordinates that one would need to have in order to specify the configuration, the entire configuration of any dynamic system at any given instant of time. And generalized coordinates are also the same. But the thing is, when you talk about generalized coordinates, the number of generalized coordinates would indeed be equal to the number of degrees of freedom for a given system. But it would be absolutely wrong to say that generalized coordinates and degrees of freedom are one and the same. Why? Because degrees of freedom is a number. So it's just the number of coordinates that you would be requiring. And generalized coordinates, when you speak about generalized coordinates, you are actually pinpointing to the exact coordinate with the name of the parameter and the symbol to specify it. Now, to elaborate it better, let me give you a simple example. Not the example that is shown in the notes. Let me take a much simpler example for you. For example, let us say that I have a spring, then a mass, again a spring, and a mass like this. Now, since we are almost at the juncture where we are done with the entire syllabus of vibration engineering, it's not very difficult for anybody of you to guess that this is definitely a system having 2 degrees of freedom. And why do you claim it to be a 2 degree of freedom system? Because in order to specify the total configuration of this 2 mass 2 spring system at any given instant of time, you must specify 2 vertical coordinates. Let us say we are naming them as y1 and y2. So in my answer to the question that what is the difference between degrees of freedom and generalized coordinates, degrees of freedom, or in short what we call as DOF in this case, is equal to 2. The answer is simply a number. How many degrees of freedom does the system have? It has 2 degrees of freedom. That's it. No mention of y1 and y2, whether the degrees of freedom are in the vertical direction, horizontal direction, are they rotational coordinates, nothing. And now when you talk about generalized coordinates, then you specify what are the variables or what are the coordinates that actually comprise your 2 degree of freedom system. So now when you mention the name of y1 and y2, you say that y1 and y2 are your generalized coordinates. So when you talk about generalized coordinates, you actually have to mention coordinates the parameters that you are taking to comprise your degrees of freedom. And when you talk about degrees of freedom, you simply mention a number saying how many degrees of freedom a system has. That's all. Whether it is a rotational degree of freedom, vertical, horizontal, translational, nothing matters in that case. But when you mention the generalized coordinates, then you definitely come to know whether your coordinates or degrees of freedom are rotational, translational, vertical, horizontal, and so on. Okay. Now, to go for the similarity in the definition of generalized coordinates and degrees of freedom, you can say that if a system has, let us say, 2 degrees of freedom, then the number of generalized coordinates would indeed be equal to 2, neither less nor more. So the number of generalized coordinates is nothing but equal to number of degrees of freedom. But generalized coordinates as such have to be mentionable variables or parameters with proper notation. Y1, Y2, theta 1, theta 2, theta 3, beta, gamma, something like that. Whatever your coordinate is, you have to mention the coordinate, and in mentioning so, you also inadvertently specify the direction in which the degree of freedom is occurring. So this is the differentiation between generalized coordinates and degrees of freedom. I hope this is pretty much clear to everybody. Now let us move on to a more formal definition of generalized coordinates. How would you define generalized coordinates? Generalized coordinates can be defined as the set of coordinates or parameters which are mutually independent in the first place. Yes, they have to be mutually independent. Okay. Which are mutually independent and which specify the configuration of the entire system at any given instant of time. So the definition almost looks very similar to the definition of degrees of freedom, because let us once again reiterate the definition of degrees of freedom. It is the number of coordinates required to specify the entire configuration. And generalized coordinates are, they are sets of coordinates required to completely specify the configuration of the system. So in the definition of generalized coordinates, you have to write it is the set of actual coordinates mentionable by their parameter notations specifically. So you have to actually mention which parameters you are taking in order to describe your generalized coordinates. But when you are describing degrees of freedom, you just have to mention a number saying that these many coordinates would be required. And nobody should ask me right now, what are the variables or what are the coordinates? You just mention that these many numbers of coordinates would be required to specify the configuration. So this is the story of degrees of freedom. And I think we have covered sufficient ground as far as the definition, the proper definition of generalized coordinates goes. Now, let us go into a few finer details of generalized coordinates. Now, somebody might be interested in asking, why don't you just call it coordinates? Because at the end of the day, they are just coordinates. You are saying X, Y, theta, gamma, beta. They're just coordinates or parameters. Why not just call them parameters and do away with it? Why should we include a very complicated name that very few people have heard? Generalized coordinates. What is the purpose behind it? Now, the reason for this is, it will be clear when we take this specific example, which I have included in your notes. So in order to make you understand the entire concept of these generalized coordinates and coordinate coupling and all, I have taken one example, although there are multiple examples that can be taken to go into the elaboration of this stuff. But in your exams also, you can focus on any one example of your own. Either you can choose to take the same example that I'm going to explain stuff with, or you can create your own example or go to the textbooks and do some extra reading and get some additional examples from there. But in any case, when questions from this topic come in your examination, you have to go for your explanations, for better explanations, with the help of one example at least. So this is the example that we are taking. Now you see, this is the ground, From the ground, I have taken a vertical spring of spring constant K1. It is passing over a pulley which is fixed at the center here, pulley of radius r, and additionally the pulley is not massless. If this mass moment of inertia I was not given, then you can claim that since no additional information is given, we can conveniently choose to ignore the mass of the pulley. That is what we generally do. But since the mass moment of inertia of the disk is given, you have to consider that also. So there is a mass element in the form of inertia of the disk itself. So maybe the disk has a mass of, let us say, capital M. Sometimes the data might be given like this. Instead of giving you the value of I, they might give you the mass of the disk itself. But in that case, you don't have to worry. Your I would be easily calculated as half of mr square, because most of you would be remembering the formula for mass moment of inertia of a circular disk about its centroidal axis to be half of mr square. So whether inertia is given directly or whether inertia is given indirectly in the form of the mass of a disk, it should not matter. But eventually what you need when a round disk like object is rotating and giving you moment of inertia, inadvertently what you need is the actual moment of inertia, not the mass. So even if mass is given, you have to eventually calculate the moment of inertia. So you know the formula, and let us move forward. So spring, then the thread which is connecting the top end of the spring, it is going over the pulley of moment of inertia I, and then another spring is connected, and then a mass is suspended. So now if you have already understood the concepts of 2 degrees or multi degrees of freedom systems, you would be very easily convinced that this in fact is a 2 degree of freedom system. 2 degrees of freedom. Okay. Now let me just elaborate a little bit more on why it is a 2 degree of freedom system, because some of you must get confused by this also. It's a sort of awkward type of system, not a very common system that you come across in your day-to-day life. Pulley is there. Suppose I do not have the second spring. I just suspend the mass here. The pulley has a mass m, and there is only one spring k1 to start with. Okay. Now you see, I need only one coordinate to specify the complete configuration of the system. Now the disk can rotate about its axis. Let us say it has rotated by an angle theta. The radius is r. So how much thread did it pass downward in rotating in the clockwise direction by an angle theta? It is r theta, right? And since this thread is being passed downwards where the mass is hanged, you can say that the vertical displacement of the mass would exactly be equal to r theta, and r being a constant. So now all that you have to do to specify the complete configuration of the system is to either mention the value of vertical displacement y, or optionally just mention the angular displacement theta of the disk. So if you give me the value of theta, I will automatically know what is y. Or on the other hand, optionally, if you give me the value of y, I will automatically come to know what is the value of theta. So in this case, it becomes a 1 degree of freedom system. Now, what we are having in our hands right now is that we have put an additional spring between the disk and the second mass. Now what happens is, even if the disk is not rotating, this second spring could individually go through an extension and give a particular displacement y to m. So now y can be produced by producing a displacement in theta, and y can be independently produced without giving a displacement theta. So in such a case where y is not exclusively a function of theta, you say that y and theta are mutually independent. And not only that, because of the presence of the second spring, now the entire system can take a lot of new configurations in which you will be struggling with specifying the configuration of the disk and the mass simultaneously. And in order to do that completely and perfectly, you must take the assistance of at least two independent variables. So this is a 2 degree of freedom system. Just by the introduction of this additional spring, you convert a single degree of freedom system into a 2 degree of freedom system. And now, this was the concept of degrees of freedom. So now that we are convinced that we are having a 2 degree of freedom system in our hands, so what do we know about the generalized coordinates? Now you say that somebody has used his mind and said, I do not like dealing with rotational variables. And believe me, there are a lot of people in this world who actually do not like rotational variables. And to a certain extent, I am also a part of that set. I am not very comfortable with rotational variables. But it has always been claimed that with certain amount of practice and dedication, you can overcome your hesitation of dealing with rotational variables. But anyway, let us take a hypothetical case. Let us take my case. I'm not very comfortable in dealing with theta. I like linear variables. So what I'm saying is, can I eliminate this variable theta from the entire picture? Instead, can I just use a benchmark? I will just put a mark on the string here. I can take a small pellet of paint and just paint a little on the thread here, and then I will say that when the system is moving, I will just record the motion of this painted part or portion of the thread, and record by how much it is moving upwards or downwards. So I am introducing a new linear variable x. And now you see, if we assume that there is no slip between the thread and the pulley, then if theta was the angular displacement of the pulley, then the linear stretch of the thread is obviously r into theta. And if the linear stretch of the thread, that means the direction of rotation of pulley is in this direction, and in this direction, when it rotates by an angle theta, it pulls the thread from the left hand side by an amount of r theta. Now, as you can see, since there is no slip, that means that this x must always be equal to r theta. Whether the second spring is in place or not, it is immaterial now. Now I'm talking about the variable x and the variable theta. So r theta is always equal to x, whether you make it a single degree of freedom system or a 2 degree of freedom system. So what I actually did was, I eliminated the rotary variable theta and put in place another variable with which I'm more comfortable. So now I say, you want to speak about the entire configuration of a system? Okay, let me give it to you. I will put a spot here, I will put a spot here, and then I will simply record the locations of these two spots, and whatever displacement this spot on the mass is having, I will name it as y. So this is one coordinate, and whatever displacement this spot is having, I will name it as x. So now I have got two generalized coordinates, and those coordinates are x and y. Again, the number of degrees of freedom is still 2, because I have x and y, that are two variables to completely specify the configuration of the entire system. Now we go to some other student or some other engineer, and we show him the same picture, and we ask him to come up with two variables which can completely specify the configuration. Now that person, let us say, is totally comfortable with rotary variables. So he doesn't even think about the presence of x. He simply says, oh yes, I see a disk, And obviously, since it's a disk, it's going to rotate. And let us say already you have given the direction of rotation in the clockwise direction. So he says that okay, when the rotation of the disk is by theta, the parameter theta will give you the configuration of the disk, and the mass is hanging, the vertical displacement y will give you the configuration of mass. So now this person gives you a set of coordinates. He says, okay, go ahead with these two variables, theta comma y. So the first person who did not like rotary variables gave you these set of coordinates. The second person who has no issues with rotary coordinates, he gave you these set of coordinates. Both the sets are mutually independent when you view it from within. From inside this set of coordinates, you have got x and y, which are mutually independent. From inside this set, when you see theta and y are mutually independent. Okay, and by saying mutually independent, please remember that it does not mean that on producing some displacement in theta, you will never get a displacement in y. That also occurs, but that does not necessarily mean that every time I produce a displacement in theta, I will always get a displacement in y. It's a very subtle difference, and people get confused. If you stop to think a lot about all these things, there is a point where you might get confused about the concept of mutual independence also. And now when you are going to discuss the coupling of coordinates, this confusion might become a little deeper. So it's better to explain the concept of mutual independence. A variable would be called being dependent on another variable only if every single instance of time you produce a displacement in the first variable, it will necessarily and compulsorily produce a displacement in the second direction or the second coordinate also. Only in that case you will say or claim that the coordinates are mutually dependent. Mutual independence is claimed by a shady notion. See, if you look at this figure, it's obvious that if I do not give the system a complete vibratory outlook, I just try to tinker with the system a little bit. How do I do that? The system is completely in equilibrium right now. I go and gently turn this wheel by a small amount of theta and do nothing else. Just hold it there. What do you think? Will y change or not? 100% y will change. Although no extension in the spring K2 will occur, but y in this case will be equal to r theta, because by rotating the disk by theta, you produced an extension in the wire of r theta. Now this extended wire will go down, and as soon as it goes down, this mass will come down by a distance of r theta. So in this case, you simply gave a change in the coordinate theta, and you automatically got a change in the coordinate y. So now some people would say, then how are they independent? If I change theta, y is also changing. But the question is this the case always? Are they actually tied together with each other permanently? That every time theta changes, is it necessary that y changes? No. Because now if I start the vibration of the system, there are two modes of vibrations. In the second mode specifically, you will see that the displacements are mutually opposite to each other. So there are a lot of instances where actually theta would be in the clockwise direction and y would be in the upward direction. So in that case, the displacement given by theta would be neutralized by the upward motion of m. And you might even see some instances when your mass is not moving, only the disk is rotating. So in such instances, theta is being produced, but y is not getting affected. So we saw one instance of mutual dependence of coordinates, but infinite other instances of mutual independence of the coordinates also exist. So if this is the case, That means when your y and theta variable are not always mutually dependent, then you can call it as mutually independent. This is the concept. Okay, so generalized coordinates, one person gave you x and y. This is also a generalized coordinate, a set of generalized coordinate, and each of these are generalized coordinates. X is a generalized coordinate, y is a generalized coordinate, and both of them together comprise a set of generalized coordinates, and the number of generalized coordinates is equal to the number of degrees of freedom. Another person gave you a set of coordinates theta comma y. These are also generalized coordinates. Theta independently, individually, is a generalized coordinate. Y is a generalized coordinate. Again, the number of generalized coordinates is equal to the number of degrees of freedom. This is the concept. So now we get the answer to the question why the term generalized in the phrase generalized coordinates. Because generalized coordinates, as we call them, can be as many as possible depending on the system. In this system, we could easily identify two sets of generalized coordinates or two sets of coordinates which do the same job of entirely giving you the configuration of the system. So if it is not a specific case that there are not a set of specific variables that are doing the job and no other set of variables can do the job, is that the case? No. So we are saying that in general, any two valid sets of variables can come and play the role of specifying the complete configuration of the system. So you say that this role is pretty much general. Any two variables are coming and doing the same job. So that is why instead of calling them specific coordinates or coordinates defining degrees of freedom or something like that, you simply choose to call them as generalized coordinates because it's a general playground. All variables are welcome. Come and play the game. That is what it is saying. So this would be the most probable reason why the people who came up with the idea of generalized coordinates named it the generalized coordinates. And now, once the concept of generalized coordinates has been cleared, I have given you the definition, I have given you the concept of mutually dependent independent variables. Why is it called generalized coordinates? And now let us go to the concept of coordinate coupling. What is the meaning of coupling? Coupling means two things which were not actually linked in any way to each other. Now you have found a way to link them with each other. Coupling can be found in pipings, wiring, and all. Coupling means basically joining together. Okay. So anything which is joined to another thing or dependent on another thing, or in a mathematical sense, which becomes a function of some other variable, you can in general say that they are somehow coupled to each other. So what is the meaning of coordinate coupling? Now, from the outlook of the English word coupling, when you develop a phrase called coordinate coupling, obviously you get the basic idea, right? Coordinate coupling must be meaning something in which the coordinates are going to get related with each other. They are going to become dependent now. This is the overall gist of the situation. So what is coordinate coupling? The coordinates within a set of generalized coordinates like this, y and theta. This was a set of generalized coordinates. So y is a generalized coordinate, theta is a generalized coordinate. Both of them together comprise a set of generalized coordinates. But up till now, there has been no conversation about any marriage between these two variables. No coupling of these variables. How are they related? We have till now we have been emphasizing very specifically on the fact that they are mutually independent. So you are actually saying something that is counterproductive to the case of coordinate coupling. You are saying that they're mutually exclusive, they are mutually independent, they are not dependent on each other. So how can they be coupled now? This is totally counterintuitive. You are saying that something can be coupled and still be mutually independent. Let us see what is the meaning of this. The coordinates within a set of generalized coordinates can either be statically coupled or dynamically coupled. So when you are talking about coordinate coupling, you are basically going to talk about two types of couplings that can occur in a set of generalized coordinates: static coupling and dynamic coupling. Now, what is the meaning of static coupling? Static coupling means that if a displacement is produced along one coordinate, then displacement is automatically generated along the other coordinates within the set. We have just covered the grounds of this particular statement. So this statement says that if I give a displacement along the theta coordinate to this disk, let us say, will I automatically see a displacement y in the vertical direction? And for this particular system, the answer is yes. And this is exactly the condition for static coupling. So static coupling within a set of generalized coordinates occurs on the basis of displacement. So you try it. You give displacement to one to the system along one direction, and you see whether displacement is automatically generated along the other direction. Now let us do the experiment in reverse. Instead of giving a small rotation to the disk, I will simply try to pull down the mass by a certain amount of distance. Now, would it imply that as soon as I pull the mass down, would it necessarily cause a small amount of rotation in the disk? Yes. If I do exactly what I have stated over here, then obviously there will be some theta without any constraints and all. And when I am not talking about vibrations or self-induced vibrations or uh, things vibrating on its own under the natural frequencies. In that case, obviously the mutual independence of the coordinates will come into play. But here, the concept of static coupling between the generalized coordinates, among the generalized coordinates, simply states that if you want to check for static coupling, you do like this. Don't think about vibrations. Don't think about anything else, what the system can do, and don't even think about whether the variables are actually mutually independent or not. You just do as the test of static coupling states you to do or asks you to do. What you have to do is you have to produce a small amount of displacement within the system along a particular given coordinate. Along a particular given coordinate means one of your generalized coordinates is theta. So producing a displacement along theta means giving a rotation to the disk. Y is another generalized coordinate within your set. Now producing a displacement along y means simply pulling the mass down or pushing the mass upwards a little bit. That's all that you have to do in this particular test. And in doing so, you have to observe whether the other partner sitting inside the set of generalized coordinates is developing a displacement automatically or not. See, you are simply moving mass up and down, okay? Whether you are pulling it down or pushing it upwards. You're not actually doing anything to the disk. You're not touching the disk. But obviously, if you move the mass up or pull it downwards, you are definitely going to see a small change in theta. The disk will automatically rotate either in the clockwise or anti-clockwise direction, depending on whether you are pulling it down or pushing it up, the mass, right? So if this is the case, then you can say or claim that your coordinates are statically coupled. And dynamic coupling goes along similar lines of explanation. The only thing being that instead of the test being on displacement, you are testing it for acceleration. Now, this is a little bit difficult to do. Because if I simply go and tell you produce an acceleration, you would be very much confused. Somebody might try to lift very gently the mass upwards, or somebody might try to pull it downward gently. Now, in that case, you're not producing an acceleration, you're moving with a constant velocity. So, giving instructions like these that go and produce an acceleration in the body, it can be a little bit confusing, although not difficult all the time, but we will come to understand better ways to find out whether the coordinates are dynamically coupled or not. But as per the definition, you have to remember the definition of dynamic coupling like this. If an acceleration is produced along any one of the coordinates, then some acceleration is automatically generated along other coordinates within the set. If this happens, then you claim that dynamic coupling occurs within the generalized coordinates. If this does not happen, you claim that dynamic coupling does not take place. Now, from the definition, static coupling is pretty much clear. But dynamic coupling, due to the presence of this acceleration term, is a little bit complicated and not very intuitive to go ahead and perform it as a small experiment on the system that is given to you. So let us explore a few more simpler techniques which will give you the answer to your problem, whether your coordinates are statically coupled or dynamically coupled, by checking some other things. Checking for existence of coupling. Now what you have to do, the first, we are discussing we are discussing three techniques of checking coupling. The first technique is to develop the Newton's equation, or to develop the equations of motion for both your mass entities. So the first mass entity is your disk, and the other mass entity is your block of mass which is suspended here. Now I'm not going to dwell on the development of Newton's equations here, because as I mentioned, we are at the completion of our syllabus of vibration engineering, and development of motions of equations for masses was actually one of the first things that were taught to you, or one of the basic things that was taught to you and then repeated over time again and again. So I will definitely not go through the motion of explaining how I apply Newton's second law of motion on the suspended mass m and come up with this equation of motion. You do it yourself. Okay. But anyway, this is the equation of motion for mass m, and this is the equation of motion for inertia body I, or the disk with inertia I. The only thing being, I have developed the equation for rotation. So I've got two equations of motion like this. Okay. I have simply rearranged it a little bit like this. This equation was rearranged in this way. This equation can be rearranged like this. Basically, what we are trying to do is acceleration term here, first variable with its coefficient, second variable with its coefficient. Similarly, here, acceleration term, one variable with the coefficients and the other variable with the coefficients. We separate the terms so that all the variables with their coefficients are separated and put here like this. Now, what is the checking rule? So the first method of checking for static coupling or dynamic coupling is, if all coordinates appear in all equations, then static coupling is there. So you check these two equations, because it's a 2 degree of freedom system, you get two Newton's equations. If it were a 3 degree of freedom system, you would have gotten three independent, or rather three equations of motion. So the first method asks you to apply Newton's law or D'Alembert's law or whatever law you know. Energy method is also there, as you can, if you remember, there were three methods actually that were taught to you for developing equations of motion. So once the equations of motions of all the masses are developed, all you have to do is you see whether all the coordinates within your generalized set of coordinates are present in all the equations. Okay, checking rule is if all coordinates appear in all equations, then static coupling is there. So let us see. First equation, our generalized coordinate set that we are using is y comma theta, not y comma x. Y comma theta is being used here. So we are going to check for this set. So in this equation, you see there is y. In this equation, you see there is theta. Again, in the second equation, you see y is present. You see theta is also present. So that as per the rule of checking, you checked whether your both variables y and theta are present in both the equations, and the answer is yes. So that means your y and theta as a set of generalized coordinates, they are statically coupled to each other. Static coupling is there. Now, how do you check for dynamic coupling? If all acceleration terms appear in all equations, then dynamic coupling is there. Now let us check to see whether this is happening or not. The acceleration terms that should be present according to this rule are y double dot and theta double dot. In the first equation, I go and check whether both of them are present. I see y double dot is present, but theta double dot is absent. So the test fails here itself. The test says that all acceleration terms must appear in all equations. And in the second equation, obviously, it is very clear. Theta double dot is present, but y double dot is again absent. So since these two equations fail the second test of accelerations, you say that there is no dynamic coupling. So based on the first test that is available with you, or the first method of confirming for checking the existence of coupling, you have come to the conclusion that my generalized coordinates are y comma theta, or rather you have chosen y comma theta as the coordinate that you like. And because these are generalized, you could have also gone for y comma x. And in that case, you will develop your equations for y and x, not for y and theta. Okay, so your equations will change. But anyway, since we are not dealing with y and x, we are dealing with y and theta. So what is our conclusion? We develop the Newton's equations for both the masses. First check is to check for static coupling. You check whether y and theta as the variable themselves appear in all the equations. Yes, it's true. So there is static coupling. And then you check for the acceleration terms of your displacement variables, whether they appear in both the equations or not, but that is false. So there is no dynamic coupling. So you say that y and theta are independent coordinates. They are my generalized coordinates. Degrees of freedom is 2. And y and theta are statically coupled, but they are dynamically not coupled or uncoupled. Got it? So this could be the end of story for our discussion, but it's better to check out two other techniques. Maybe you find this as the simplest of all techniques, but some people might find other techniques more satisfactory, because some people do not dwell on the equations of motion too much. They simply directly go for the matrix equations. And I have even taught you shortcuts for constructing matrix equations quickly. So there might be people who will simply look at the system and they won't even go for Newton's equations. They will simply jump on the wagon and they will just quickly start constructing their matrices. They will construct the mass matrix, they will construct the stiffness matrix, and quickly go on with the development of frequency equation. So for those people who don't even bother to construct Newton's equations, the second method is for those guys. So what you do is, and if you are wondering how do I make the matrix equation that is shown here, I have taught you this also in great detail. But a hint for you guys is that it can be constructed from these set of equations directly. Now you see, what are the masses? What are the mass terms actually? In this particular case, one of the masses is specified as a mass term and the other mass is not specified as a mass, but it is specified as a value of moment of inertia. But even in such cases, you don't have to bother with the finer details. You can simply construct your mass matrix as a diagonal matrix. For example, I'll just show you how to do this for a 2 degree of freedom system, a general 2 degree of freedom system. See, this was taught to you that if you have a 2 degree of freedom system like this M1 and M2, then the mass matrix without giving much thought can simply be constructed as a diagonal matrix in which the mass entries are put along the principal diagonal and the rest of the elements within the matrices are made zero. This is a direct method of constructing the mass matrices. Now, in your problem, you don't have two masses, but you know what are the mass entities. One mass entity is I, the second mass entity is M. Now you can claim either one of them to be the first mass and the other to be the second mass. In this case, as you can look into the mass matrix, I have taken, or rather I have decided to take the mass itself as the first mass element and the inertia element as the second mass element, and I have put them along the principal diagonal, and I simply claim that I am not going to make the Newton's equation. I just constructed the mass matrix. Done. Now what is the mass matrix going to be multiplied with? You already know that for a single spring and mass system, the differential equation of motion is like this. Now if I put it in matrix format, all that I have to do is construct matrix boxes outside this. That's all. Now instead of these things, the mass matrix, instead of being a single variable M, it is a matrix of multiple masses. That's all. But the structure of the equation is exactly the same. It is easy for you to remember. You see, what is the difference between this equation of motion, which is for a singular mass, and this equation of motion, which can actually embody infinite number of masses? This equation, this matrix equation, can literally contain within itself one mass, two mass, 100 masses, 10,000 masses, millions of masses, depending on what your situation is. This is the matrix equation. But see the one-to-one correspondence here. M matrix, X double dot matrix, K matrix, X matrix, 0 0 matrix. It's very easy to remember like this. So now all you have to remember to construct the matrix equation is that M matrix will always be a diagonal matrix having only diagonal entries. The rest of the elements will be zero. The acceleration matrix will be simply a vector, a column vector containing the acceleration variables of your problem. Now, what are the acceleration variables of your problem? It's y double dot and theta double dot. So that's exactly what we do. We place your y double dot and theta double dot with the correspondence of the same order in which you treated the mass elements. Since you took m as the first mass element, so the acceleration of m, that is y double dot, will be treated as the first element of your acceleration vector. Similarly for I. So we constructed the acceleration vector, that is y double dot and theta double dot. And now what do we do for the K matrix? This is the toughest part. And this is the part where you actually have to remember some things. The zero matrix will be simply using the number of degrees of freedom and putting equal number of zeros inside the column vector. Similarly, just in the manner in which you constructed the acceleration vector, you construct the displacement vector. What is the first acceleration term? Y double dot. So the first displacement term would be y. What is the second acceleration term? Theta double dot. So the second displacement term would be theta. That's it. Now the only mystery that remains is how to construct the K matrix. One thing is sure, the size of the K matrix would be exactly matching the size of your mass matrix. So if your mass matrix is a 2 by 2 matrix, your K matrix is also going to be a 2 by 2 matrix. Now what do you do in order to construct the K matrix quickly? There are many methods, but as I told you, if you already have your equations in hand, then your K matrix can be constructed from here directly. Now, let me just rewrite these equations on my whiteboard over here, and then I'll show you. Please be patient with me. I'm just rewriting this equation. The first term is my double dot. My first variable is y, and the second variable is theta. Keeping this in mind, I will take the first equation as it is. So my double dot plus k2y minus k2r theta equal to 0. We have to remember to leave the right hand side of all equations equal to 0. Second equation, I will make a small rearrangement. Let us see what I'm going to do. The acceleration term obviously has to come first in all equations. So I will keep it as it is, I into theta double dot. Now instead of taking this as the second term, I will take this as the second term. Why? Because I want to have a correspondence and the same order in which I took the first equation, because I am treating the y variable first and then theta variable second. So I will take this here and take this term here. I'm just putting that, I'm just shifting them, or rather switching their positions. That's all. I'm not changing anything else in the equation. So I write this first. So this is minus k2 ry, then the first term, that is plus k1 plus k2 r square theta, and the right hand side is 0. So now this is how these two equations simply rearranged to look like this. And now you see the acceleration terms are lined up, the displacement terms are lined up. You see this? This is why I rearranged it like this. And now all that you have to do is, you have your mass matrix, you have your acceleration matrix. For the K matrix, you simply pick up these terms from the structure of this equation. Just look at this part as a whole. So obviously the first term is k2y, so it's k2. The second term is minus k2r theta. So the second term inside the K matrix will be minus k2r. This term is minus k2ry. So the term inside the K matrix would be minus k2r. And here it's k1 plus k2 r square theta. So I will leave the theta out and it will be simply k1 plus k2 times r square. This is my K matrix. So if you have the differential equations of motion, it's very, very easy to construct the K matrix. And obviously after that, your displacement vector will be y theta equal to 0, 0. This is what you have. So this was basically a revision of what you already know, how to construct this. Some of you must be remembering, we have already studied this. So if instead of individual equations of motion you have in hand. Somehow maybe somebody gave you ready made, they gave you the matrix form of equation, and then they asked you the question, guess or try to find out what type of coupling your generalized coordinates have. How do you do that? Now the checking rule for matrix form of equation is, if the mass matrix is diagonal, yes, it is diagonal, it is diagonal, then no dynamic coupling. So all you have to do is construct the mass matrix. You don't even have to, if somebody asks you to just go ahead and check for dynamic coupling, whether it is there or not, then you don't even have to construct the rest of these matrices. You just construct the mass matrix and check whether it is diagonal or not. Yes, it is diagonal. So you say there is no dynamic coupling. So that means if there is some other numerical value sitting at the other parts where usually zeros creep in, then you say that there is dynamic coupling. Otherwise, in most of the cases, when you simply see a diagonal mass matrix, you say no dynamic coupling. And once again, if stiffness matrix is diagonal, then no static coupling. Now look at the stiffness matrix. Is it diagonal? Absolutely not. Because if it were a diagonal matrix, the entries would only be placed on the diagonal, the principal diagonal. Here would be 0. You will get a 0 here also. But since these two entries are not 0, so we obviously know that your stiffness matrix is not a diagonal matrix. And if it is not a diagonal matrix, then static coupling is there. Because the rule says, if the stiffness matrix is diagonal, then no static coupling. So we have a case which is opposite to the stated rule here. Your stiffness matrix is not diagonal, so you have static coupling. So once again, looking at the rules of the matrix format of equation, you get the same result. Because from the first type of testing, you already have the answer to your problem, that if my coordinates are y and theta, then I checked for coupling and I found that y and theta are statically coupled, but they are not dynamically coupled. So this answer is once again obtained from the second alternative test. Now please remember, test number 1 and test number 2 are alternatives to each other. Don't think that if somebody asks you for coupling, you have to do both tests. Either you go for test number 1, give your conclusions and close the case, or you go for test number 2, then give your conclusions and then close the case. So test number 1 and test number 2 are alternatives. Don't think that you have to do all the tests. Okay, and similarly, the third test is again an alternative. Now what you have to do for third test is, now this test is based on potential energy and kinetic energy observations. Okay, so the first test was construct the equations of motion and then test for coupling. The second test was construct the equation of motion in a matrix format and then test for coupling. The third test is develop the expression of total kinetic energy of the system and develop the expression of total potential energy of the system. Now the third test, the third alternative rather, I would say, it is based on energy expressions. So what do we have to do? Let us look at the figure now. What is the total kinetic energy of the system? For kinetic energy of the system, all that you have to do, kinetic energy is very easy to make. Okay, so if you are claiming that your instantaneous displacement of mass m is y, then it's very easy to say that the instantaneous velocity would be y dot. Just put a variable like that. And if you say that the instantaneous angular displacement of your disk is theta, what is the instantaneous velocity? You simply say theta dot. That's it. Are you giving me the value of theta? No. Are you giving me the rate of change of theta? No. So how should I know? I will simply say that it's just like claiming what is the velocity. Velocity is v. That's all. So if theta is the variable, my angular velocity is theta dot. If y is the displacement variable, then my velocity is y dot. That's all. And if there are only two mass elements, the first mass element and the second mass element, then what are the kinetic energies? Half I omega square. See, this is omega. Okay. This is basically omega. And this y dot is basically linear velocity v. So what is the kinetic energy for mass m having instantaneous velocity v? It's half mv square. What is the rotational kinetic energy of inertia element I having instantaneous angular velocity omega? It's half I omega square. So what is the total kinetic energy? It's very easy to state. It's half mv square plus half I omega square. That's it. So we have developed the expression for total kinetic energy of the system. Now, what is the total potential energy of the system? This is a very tricky situation. Actually, I'm claiming that not very, not many people know how to develop the proper expression for potential energy. It's very confusing. I'm directly claiming here. But nevertheless, I'm not going to explain the entire thing. I'll just give you a hint. See, in an instantaneous scenario, for calculating the total potential energy of the system, what you have to do is you have to first declare one state of the system as the zero energy state. Now, which is that state which you choose to declare as the zero energy state? That is most commonly the position of equilibrium. So let us say when this system is statically in equilibrium, so obviously K1 spring, is it stretched or not while it is in equilibrium? Yes, there is a static stretch which is called a static displacement delta 1. Is the second spring stretched or not? Yes, it is also stretched by a static displacement delta 2. So already some potential energies are stored inside the springs. And initially, when this mass was separate and you were just bringing in to attach it over here, at that time, this was not the level of the second spring. It was somewhere up over here. And when you attached the mass, your mass actually came down by another static displacement delta. So some potential energies were already in play when you were simply constructing the system. So what happens? From the general equilibrium position, when you start your calculations for potential energy, what happens to the potential energy of the spring that is already stored? What happens to the potential energy of the mass that is lost while it comes down by a displacement of delta? Do we consider them or not? This is the first confusion that you must overcome. And in order to wipe out all these doubts, what we do is we simply state, I see the system is in equilibrium right now. Okay, in the back of my mind, I know that there is some sort of stretch being experienced by both the springs, and initially the mass had come down and all that stuff. But whatever the situation the system is finding itself in right now, I consider that the potential energy, the entire potential, I am bundling up all the potential energies, the potential energy of the spring, the loss of potential energy of the mass, everything. I say that everything is 0, 0, 0. No questions asked. Now, if there is any displacement or any further stretch of the springs and the masses, whether they climb up or climb down and on so on and forth, only in that situation I say or claim that there is some potential energy lost or gained. So from the equilibrium position where I consider all the potential energies to be zero, what will be the potential energy stored in the entire system when in an instantaneous position your disk has rotated by an amount of theta and your mass has overall come down by a distance of y? What is the potential energy? I leave it as a homework and as a rigorous brainstorming exercise to you. The total potential energy of the system will be given by this expression. I have given a hint also, so that you can play with the variables and come up with this expression. Now the challenge for you guys in this problem is, you don't see the loss of gravitational potential energy of the mass, although it is coming down by a distance y. You see, I am claiming that from the equilibrium position of the mass must have been somewhere around here. This was where the mass was actually hanging. Now, once the whole system starts vibrating, I took a random position in which the mass is occupying a position y distance below the equilibrium position. So actually the mass has lost some potential energy. It has lost a potential energy equal to mgy, and this must appear with a negative sign. Where is this expression in your total potential energy? It is not there. And as a matter of fact, all that you can see is half k into square of displacement, half k into square of displacement. So if you look at the overview of the structure of the potential energy expression of the system, you will see that I have conveniently ignored the loss of potential energy due to the mass coming down by a clear distance y. Now that is up to you. It's a challenge. The only hint that I will give is this. You can take up a small research, I would say. Go and search on the internet and search your textbooks and find out why this eventually comes out as the correct expression for total potential energy of the system, in which the loss of gravitational potential energy due to the mass coming down will eventually get cancelled out. So anyway, let us start fresh with the fact that I have in my hand the kinetic energy expression for the entire system, and I have in my hand the total potential energy of the system like this. Now, this second expression is nothing but the expanded version of this one. That's all. I just expanded the squares and all, and I got this expression. Now, what is the checking rule over here? The checking rule is, if the kinetic energy expression contains any sort of product between the coordinates. So what this checking rule is asking you to do is construct the kinetic energy expression and observe the terms inside it. Do you find any term in which either the velocities or the accelerations or the displacements within your generalized coordinate set are getting multiplied with each other? Do you find it? I see y dot getting multiplied with y dot itself. I see theta dot getting multiplied with theta dot itself, but I do not see any instance, I do not see any term in which I see a marriage between y and theta, y dot and theta dot, and y double dot and theta dot. And if this is not there, then dynamic coupling does not exist. So the rule says that if such marriages occur in your expression, dynamic coupling exists. And since such combinations are not present in my kinetic energy expression, so I say that dynamic coupling is not present in my coordinate system y theta, or the set of generalized coordinates y and theta are not dynamically coupled. Now what is the check for static coupling? The same sort of check, but in this case you have to check inside the potential energy expression. So now remove the kinetic energy expression from your data set, you go to the potential energy expression, this is it, and again check each and every term whether the set of generalized coordinates are getting mutually multiplied or not. I see y into y, so no mutual multiplication of y and theta. I see theta into theta, again no mutual multiplication of theta and y. But here we find the culprit. You see, these two have married and settled down peacefully. Y and theta are multiplying with each other. If this has been found in any one term inside the entire array of the expression of potential energy, then you say that static coupling exists. So if somehow just one term wasn't there, this term, if somehow it wasn't present in the potential energy expression, if only this much was the potential energy, I'm just taking a hypothetical case. Okay, this obviously is there, but for the moment, let us just ignore and let us just assume a condition where this was not present. In such a condition, if I had only these two terms, then I would say that my generalized coordinates y and theta are neither statically coupled nor dynamically coupled. That is what I would say. Because for dynamic coupling, I have to see a marriage between y and theta in the kinetic energy expression. For static coupling, I have to see a marriage between y and theta in the potential energy expression. So if such marriages, such products, mutual products or mutual multiplications are not there in both the expressions, then I say they are neither statically coupled nor dynamically coupled. But what is happening here in our system? Dynamic coupling is not there, but due to this term in the potential energy expression, you see a marriage, y and theta are getting multiplied. So you say कि एक मछली ने पूरे तालाब को खराब कर दिया, कह सकते हो. Just because of this single term, your entire potential energy system becomes the culprit. And now you say that yes, there is static coupling. So once again, even the third test, which is once again I state an alternative test. तीनों टेस्ट नहीं करने हैं आपको एग्जाम में, तीन में से कोई सा भी एक करना है कपलिंग चेक करने के लिए. And we have tested our system using all three tests just for the sake of demonstration, and we have all the three times we have come to the same conclusion. What are the conclusions? That if your generalized coordinates are y and theta, they are statically coupled, they are not dynamically coupled. This is the conclusion that you derive from this. So unfortunately, no question has been asked from this topic in your RTO exam. So what can be expected of you? If you are fortunate or unfortunate, depending on your standpoint, if a question does come in your examination, what would that be? I see a possibility of the definitions being asked. What do you understand by coordinate coupling, generalized coordinates? And a very common type of giveaway in RTO exams is write short notes. So if you are asked to write short notes, take an example like this, construct the equations, and just put down any one checking rule. You don't have to put down all the checking rules. Now, once again, that would depend on the weightage of your question. If your question has sufficient weightage, then you can go and explain all the three rules, all the three methods. If your question has a little less weightage of marks, then you just suffice with one checking rule, any one of them, whichever you please. Put in some diagrams and all. Whenever short notes and explanation type questions come in, it's better to put in some diagrams. That is always beneficial. And on the most extreme end, you can also expect a question like this. Somebody might actually construct a system for you. Need not be the same thing. It could be something else also. And then actually ask you to develop the equations of motion on your own and then perform some check on it and to come up with your own conclusion whether the given system is statically coupled or dynamically coupled. Give your reasoning for that. So with this lecture, I hope I have sufficiently explained all the techniques and all the concepts that you need to address any type of problem in your exam. So with this, I would just say best of luck. And this was the last lecture of this entire lecture series. So once again, best of luck and thank you.